We now combine all of the elements that we have seen in this chapter that model different parts of the operation of a battery cell, and we combine them into a single model that we call the Enhanced Self-Correcting Cell Model, or ESC cell model. That is my name for it. This is not a universal name, so I will use this term in this course, but in the literature, people would probably simply call this an equivalent circuit cell model. The reason I called it this was historic. This model is enhanced because it includes a description of hysteresis where earlier models did not have any description of hysteresis. And it's called self-correcting because the model voltage converges to open circuit voltage plus hysteresis when we're resting, and to open circuit voltage plus hysteresis minus these IR terms on a constant current event, which again was somewhat different from some previous models that had been used by myself and in the literature. So this is a good feature because that's what the true cell does, and if the model converges at least in these boundary cases, the resting case and the constant current case, that means that your application in those examples too will also converge in its behavior to how it should converge in those special cases, even though it may not converge precisely all the time. There are things you can do to force it to be right. Here's the enhanced self-correcting cell model drawn out. I have open circuit voltage as a function of state of charge. This is a controlled voltage source where Z of t is the variable that controls the voltage out of the voltage source. There's a hysteresis component. There's an equivalent series resistance, R0, and there is usually at least one resistor-capacitor pair. It's possible for there to be more resistor-capacitor pairs, and when we are modeling diffusion later on in the semester using a physics model, we'll see that the diffusion processes in this cell really can be modeled perfectly only with an infinite number of resistor-capacitor pairs. So if you are a purist, you will need a very big piece of paper to draw all those. But in engineering reality, it turns out that one resistor-capacitor pair does quite well, and usually with only 2 or 3 you can do as well as you need to do in some application. So certainly you don't need hundreds of these. A very small number of resistor-capacitor pairs should be adequate for most applications. If I do have more resistor-capacitor pairs, how does that change the model? Instead of, in my IR equation, instead of having a single value of current through a resistor, I'm going to have multiple values of current through resistors because I'm going to have multiple resistors. I'm going to have a circuit with one resistor and another resistor and so forth. This is R1, that's R2. So I'm going to have an IR1 and an IR2 in the model. And we refer to that as I sub R, where I sub R is a vector that has as many components in the vector as I have these RC pairs. And the model that we've developed a couple sections ago can be generalized, and the current through those resistors at time step k plus 1 is equal to their exponential time constant factor multiplied by the current through those individual resistors at the previous time steps. This A sub RC is a matrix. It's a diagonal matrix, meaning that one resistor current is not a function of any other resistor current. It's simply a function of its own past and whatever the overall cell current is that's driving it. Here is the rest of the equation wrapped around on the second line. I add to the self-decay of the RC circuit, which is what the first line is, the forced part due to the input current, which is the 1 minus e to the minus delta t over RC for the particular resistor-capacitor combination that we're looking at. This is the B sub RC vector. I can put these expressions together into one matrix expression form, which can be convenient for computer computations. So I will define a hysteresis A matrix, which is the coefficient that we saw on the previous section, this e to the minus absolute value eta I gamma delta t over q. That was the hysteresis time constant. And combine all of the equations that we have seen that describe the internal dynamics of our equivalent circuit model. This says state of charge at time k plus 1 is 1 times state of charge at time k plus 0 times IR plus 0 times H, and then minus eta delta t over q times input current. That's exactly what we saw before, and that is part of this model. Then it also says I sub r, that could be a vector stacked there. That's not necessarily just a single number, that could be multiple, is 0 times state of charge, but A sub RC times I sub r, like we saw just now. And then plus B sub RC times input current, like we saw now, plus 0 times the sign of the input current. Finally, the hysteresis voltage is A sub H times the previous hysteresis voltage plus A sub H minus 1 times the sign of the input current. All right, you'll notice that there was a minus minus in here. This used to be 1 minus AH, but if you go back and look at it, it was subtracted out. So if I need to add it in, it's plus A sub H minus 1, and the equations agree. All of this together, this matrix equation is called the state equation and describes the dynamic effects of the circuit model that are attempting to match the dynamic effects of the real model. This is the state equation. The output equation or measurement equation computes cell voltage. If I go back to the circuit picture, we would look at this and say cell voltage is open circuit voltage plus hysteresis minus this, treating hysteresis as a voltage source and not a voltage sink. And you could treat it either way, you just have to be careful of the signs that you're using in your equations. So the voltage is equal to OCV as a function of the state of charge and temperature, which I extract out of the state equation here. So Z of t is the first component of the state that I'm simulating using that equation, and that gets plugged in here. And temperature is something that I either model with additional states or I measure, and usually we have a measurement of temperature. The hysteresis voltage, like we saw, is M0 times the instantaneous hysteresis, SK, then plus M times HK, where H of K, again, is from that state vector, the last component, minus the voltage drops over all of the resistors in the resistor-capacitor network, so minus the sum of Rj times I sub Rj, where the I sub Rj are the components of that vector, and then finally minus cell current I times R0. So these two equations together with associated parameter values filled in give us what I call the ESC, Enhanced Self-Correcting Model. All the parameter values, by the way, are non-negative. They're either positive or 0 in these equations, and that's a constraint that we can impose when we are trying to find the parameter values of these equations. At this point, we have developed the model. We have derived the equations of the model, and in order to use the model in a simulation, we would need to find those parameter values. I would need to know everything in these equations. I would need to know what is the open circuit voltage relationship, what is M0, M, Rj, R0, what else do I have in here? I've got a coulombic efficiency, I've got a capacity. So all of these numeric values in these equations need to be tuned or found or measured or estimated from a real cell using some process. And for the remainder of this chapter, our focus is going to be on how do we find those values. And we're first going to look at how do I find the open circuit voltage relationship of this cell. So to find specific numeric values for the model parameters, we have to perform experiments on the cells of interest. You need specific equipment that can control the input current to the cell while at the same time measuring the voltage of this cell. You need equipment that can maintain the ambient temperature of this cell, so you've got a constant temperature environment, so you have model parameters that apply to the dynamics of the cell at different temperatures. When I'm looking at the open circuit voltage, this is a static function of SOC and temperature. It's not a function of time, it's only a function of those two inputs. You could argue that as the cell ages, this function will change a little bit, and it does. We're not going to get into that here, although we will develop some ways of understanding that in the physics section of how that might change. But it turns out not to change very much. It changes, but not very much. The big inputs to the open circuit voltage relationship are state of charge and temperature. After that, it's static. The other aspects of the cell performance are dynamic. We got the resistor capacitor networks where the voltage changes as current is applied and removed, and it's not an instantaneous effect. And the hysteresis changes as state of charge changes, and the IR voltage changes as the current changes. So there are two completely different types of cell tests that are performed. One type is to collect the static information of open circuit voltage, and the other type is to collect the dynamic data for everything else. And we're going to talk about the OCV relationship first. Our goal is to find what is the voltage of the cell, the resting voltage at every state of charge. And one approach would be to start with a fully charged cell, and then discharge a known amount and let the cell rest and measure the voltage. Discharge, rest, measure, discharge, rest, measure, and when you do that, I would get a sequence of points that would tell me what is the rest voltage, which we'll call OCV, as a function of, in this case, depth of discharge, how many ampere hours I have removed from the cell. The results we get from this test would be quite accurate as long as I rest a long time before taking my voltage measurement. But it gives me only a finite number of points, a certain, at least a discrete number of points, and I don't know for certain what OCV is in between those points. So I prefer a slightly different approach, where we are never really quite resting. We are going to discharge the cell slowly, where it's being so slowly discharged, I'm almost in equilibrium at all points in time. And as I do that, I'm going to measure the voltage. It's going to look something like that. And then I'm going to charge the cell slowly and measure the voltage. It's going to look something like that. And the average at every state of charge, the average of those two curves is what I will take to be the open circuit voltage relationship. So somewhere in between here is the actual open circuit voltage of this cell. And that's something that we can do quite easily in a lab test. We just slowly discharge and measure a bunch of voltages, slowly charge and measure a bunch of voltages, save those to a data file, use MATLAB or some other program to load in that data file, compute the average, and I get a nice open circuit voltage relationship. Now there are some subtle points that are necessary to understand to do this well at different temperatures, so let's go through the process in some detail. This is what we actually do. What I just mentioned, what I just told you was the idea, but this is the refinement of the idea. Here we have in this procedure of Vmin, which is a minimum voltage for this cell, and Vmax is a maximum voltage of this cell. And the cell manufacturer will provide these voltages. And the definition or the application of these voltages is that this is equal to the rest voltage of the cell at 25 degrees Celsius, which is room temperature, at 0% state of charge. And this here is similarly the rest voltage at 25 degrees Celsius at 100% state of charge. So the cell manufacturer will tell us what voltages to expect for 0 and 100% state of charge only at room temperature. I have never seen them tell you what those voltages are at any other temperature. And that's why there are some subtle details in these tests. We break the testing down into test scripts. And a script is like a program, and your test equipment, whether you get it from Bytrode or Arbin or some other company, your equipment will have some ability for you to program how it operates, and so we call those a script. To do this open circuit voltage testing, using the way that I will tell you, requires 4 different programs, 4 different test scripts. And the first one, we start the cell at 100% SOC. I should mention that there. So start at 100% SOC. How do I know I am there? The manufacturer will tell me how to charge a cell. And it's going to be at 25 degrees Celsius. I have to charge the cell up to this Vmax with some other cutoff conditions, but I will follow the manufacturer's specification for charging the cell to 100% at room temperature at 25°C before I begin. Then, in script 1, I soak the fully charged cell, so that's our starting condition, at the test temperature. Maybe I'm trying to find OCV at 0 degrees Celsius, so I set my thermal chamber to 0 degrees, and I soak the cell at 0 degrees for at least 2 hours to ensure a uniform temperature throughout the cell before I do anything. If you've got a really big, thick cell, maybe you want to do it more than 2 hours, so it's your call. But we just want to be really sure that because we're looking for what is the OCV at 0 degrees Celsius, I need to make sure the cell really is at 0 degrees Celsius before I do anything. After I am convinced that the cell is at the right temperature, I will discharge this cell at this constant current rate of C/30 until the cell terminal voltage equals the manufacturer specified Vmin. And that will be on the order of a 30-hour operation. Notice that if I am not doing script number 1 at 25 degrees, if I am doing some other temperature like 0 degrees, when I arrive at Vmin, I am not at 0% state of charge. I have, in fact, no idea what percent state of charge the cell is at right now. And in order to figure out what the state of charge is at this point here, at the end of step 2, I need to return the cell to 25 degrees Celsius and then discharge down to Vmin to have a calibrated 0% SOC point. So Vmin tells you over here, remember, Vmin tells you the 0% SOC point only at 25 degrees, only at room temperature. So here at my test temperature, I don't know what Vmin means. I only know that I'm not supposed to discharge lower than that in voltage. So the script number 2, this is the second cell script that I run, is to soak the cell at 25 degrees for at least 2 hours, again, to ensure a uniform temperature. If the cell voltage happens to be below Vmin, don't worry about that too much. I don't think I've caused any damage. It's not going to be very much below Vmin. but then charge the cell at a slow rate, like C over 30, until the voltage is equal to Vmin. Or if the cell voltage is above Vmin, then discharge until the voltage is equal to Vmin. So the idea here is I want to figure out how much charge I need to add or subtract from the cell in order to bring the cell to 0% SOC. I started at 100%. Right here, I now know I'm at 0%. In this process, I know how many amp hours were removed from this cell. In this process, I know how many amp hours were added or removed from the cell. And the sum of those two things is going to be the capacity of this cell. And once I know the capacity and I know the ampere hours at any time, the depth of discharge in percent is equal to the amp hours discharged divided by the capacity. That's the basic idea that we're going to use later on. And then I will have a voltage versus depth of discharge relationship. And SOC equals 1 minus depth of discharge. And so I also have voltage versus SOC for the discharge portion of the test using script 1 and script 2. That's the first half. The second half does the same thing, only charging. So I return the cell to the test temperature for at least 2 hours, and I charge the cell at a constant current rate until the cell terminal voltage equals Vmax. Now I know I begin this at 0%, but I have no idea what state of charge is when I achieve Vmax because, again, Vmax corresponds to 100% SOC only if I'm resting at room temperature, and I'm not. I'm at some other temperature, the test temperature. So I have to have a step 4. Step 4 says, again, soak the cell at 25 degrees for at least 2 hours. If the cell voltage is below Vmax, then charge until I get to Vmax, and if it's above, then discharge. Finally, at the end of this test, I am back at 100% again. As we are conducting these experiments, we continuously monitor voltage, accumulated ampere hours discharged, and accumulated ampere hours charged. Perhaps once per second. This is a slow test, so maybe even once per minute is adequate to do this. Because we are using a very low current, then there's almost no heat generation. I don't think it would be measurable except by the most sensitive of equipment. And so we could consider that all of the data points collected at the test temperature, where the thermal chamber was set to the ambient test temperature to correspond exactly to that test temperature, and all data points collected for the 25 degrees Celsius ambient test point to be equivalent to that. However, if you really want to be careful, you can attach a thermistor or a thermocouple to your cell and measure temperature data as the test progresses to verify this assumption. In these two plots, I illustrate some data that we collected in the lab that shows the discharge portion of a curve for a cell and the charge portion of a curve for a cell for this test. And the first 2 hours, I started to remember with a fully charged cell, and for 2 hours I rest at a test temperature, and there's a small change in voltage. And then there is the discharge relationship. And this did not last for 30 hours. I said use a C over 30 rate, and this lasted only, well, about 2 plus 23 hours, maybe, no, 2 plus 25 or so. So the nominal capacity of this cell was used when we designed the test, but it turned out the actual capacity of this cell was below that because this was an older cell that had already been used in some application before I did this testing. And so I got, instead of the C over 30, I thought I was getting, I really got about a C over 27-ish result. And that's okay. The C over 30 is not magic. The C over 30 is chosen only to give you a slow discharge and a slow charge that are close to equilibrium at all points in time, so that I can interpret the voltage that I measure as being close to the open circuit potential, or open circuit voltage rather, although it's not going to be exactly that. Again, in step 3, there's the 2-hour rest at the test temperature where the voltage is changing a little bit as the cell temperature equalizes, and then we do the charge portion. And again, it's not a 30-hour charge. It's the same cell here. It's not 30 hours because the capacity of the cell was lower than the nominal capacity. In the next sections, we'll look at a couple of things like how do I find the coulombic efficiency first, and then how do I create an open circuit voltage relationship. Before we get there, I want to point out that if you were to take this figure and try to overlay it on this other figure, you would, first there's some missing parts of step 2 that would shift the curve over a little bit, but if I overlaid, I would get something like this, and I'll have the actual picture later on. And I will compute, roughly speaking, the open circuit voltage to be in the middle of these curves. There are some tricky parts, like, well, what about in here where there is no middle, and what about in there where there is no middle? And we need to find a way to be able to account for that. But the idea basically is I discharge slowly, I charge slowly, I measure voltage, I take the average, and that will be the open circuit voltage relationship. And there are these minor modifications to get as accurate a result as we can. So with that idea in mind, let's proceed and talk about analyzing this data to find the information that we really need.